2.7. Apply the fundamental theorem of algebra in Algebra 2. Zeros, factors, and solutions. If k is a zero of a polynomial function, it is also the solution of f of x equals 0. And x minus k is a factor. So if I have that 2, if that's a 0 of the polynomial function, that means that f of 2 equals 0, and that means that x minus 2 is a factor of the polynomial. If I look on the graph, that would mean my graph would cross the x-axis at positive 2. So here is the fundamental theorem of algebra, and emphasis on the fun. Counting complex, which would be imaginary, and repeated solutions, an nth degree polynomial has exactly n solutions. So what these would look like on a graph is, suppose I have a function that goes back and forth like this. So that would cross the x-axis in 3 places and would most likely be a cubic function. But what if I move this cubic function up? So it only crosses in one place, but then just touches the x-axis and goes back up. Well, technically it only touches in 2 different locations, but this place here where it touches and then goes back up, that would create a repeated solution, which would create 2 of the same factors. Or if that was at 3, then the factors would be x minus 3 times x minus 3, or x minus 3 squared. So cubic function, 3 real zeros here, versus 2 real zeros here, but one's a repeated 0. So again, if we count the repeated solutions, that would still be a cubic 3rd degree polynomial. Or what if we had something like this, where it only actually crosses in one location? Well, what would happen there is we would have 1 real solution, and then we'd end up with 2 imaginary solutions, still giving us a 3rd degree polynomial. So down here, if we look, how many solutions does an equation like this have? Well, I just want to look at the degree. This is 4th degree, so it's going to have 4 solutions. Now again, those 4 solutions include complex solutions, repeated solutions, along with the real solutions. How about this one? How many zeros does the function f of x have? Well, this one's 3rd degree, so it will have 3 zeros. Remember, zeros are the same as solutions. And that is the fundamental theorem of algebra. So if you're asked to find all the zeros of a polynomial function, we want to start like we did in the previous section with the rational zero test. So factors of the constant term, 6, being 1, 2, 3, and 6, divided by factors of the leading coefficient would just be 1. So there I have 8 possible rational zeros. So I'll go through and plug them in. Let's start with f of 1. And I could either use direct substitution or synthetic substitution. Go ahead and plug in f of 1, see what you get. And remember, if you do have a graphing calculator available, you might want to use the table feature to find out which ones equal 0. When you plug in 1, you should get 0. So there's our first 0. I might go through and plug in the rest of the positives, then go back and insert the negative, or vice versa. If I plug in 2, I get 12, so that's not a 0. Plug in 3, you should get 120, so that's not a 0. Plug in 6, we get 5,400, definitely not a 0. And let's go back to the negatives then. If I plug in negative 1, I get 24, so that's not a 0. Plug in negative 2, we do get 0. So it looks like there's another rational 0 of negative 2. Now, As soon as I find one that works, I might want to go ahead and start using synthetic division to start narrowing down my options. So let me clear some space to do that. So let's set up the synthetic division. I could start with either the 1 or the -2. It doesn't matter which one I start with. Let's just start with the 1. And when I write out my coefficients for the polynomial, make sure in this case we need to include a 0 because we skip over x cubed. So I have 0x cubed, 8x squared, -13x, +6. And again, if you're missing even the constant term, you would need to put a 0 in for that. Let's do the synthetic substitution. And again, I should be getting 0 for my remainder. Confirms I did that correctly. And now, like we did in the previous lesson, let's take our other 0 into that remainder. Well, the remaining coefficients without the remainder on the end. So once again, the process of adding and multiplying. So multiply -3 times -2, add in this column, multiply, add, multiply, add, and once again we get a remainder of 0, so that's a good sign there. Now I'm down to a 4-term polynomial. I start out with x to the 5th. This would be x to the 4th. So now we're down to x cubed. Since I'm not yet down to a quadratic equation with 3 terms, I can't use the quadratic formula at this point. So I'd want to try factoring by grouping. Now, I can see if I group these two together, I'm not going to be able to factor out the same factor as with these. Or I'm not going to be left with the same factor if I were to factor those. Again, we can look at that a little closer. So I'd have x cubed minus 3x squared plus 5x minus 3. If I group the first two terms together, I could factor out x squared and be left with x minus 3. From the second group, I couldn't factor out anything, just a 1. So I'm just left with 5x minus 3. Well, this factor does not match with this factor, so I'm stuck at that point. I cannot factor it by grouping. So what that tells me is, because none of my other zeros worked, I might end up having a repeated 0. So maybe 1 works more than once and is a repeated solution, or maybe -2 does. So with what I'm left with down here, I'm going to try +1 and -2. All right, so let's try +1 into what I'm left with here. So synthetic substitution one more time. Bring down the 1, multiply, add, multiply, add, multiply, and I do get a remainder of 0. All right, so it looks like 1 is a repeated solution, meaning that my graph will touch at 1, but either come down, touch at 1, go back up, or come up below the x-axis, touch at 1, and go back down. So far I'm up to 3 zeros, but I'm asked to find all zeros, and according to the fundamental theorem of algebra, that means that there are 5 zeros. This does count as 2 separate ones. It's a repeated solution, but does count as 2 separate zeros. So I need to find 2 more. Well, the good news is I'm now down to a quadratic equation, and quadratic equations we can solve by using the quadratic formula. So I have x squared minus 2x plus 3, set that equal to 0, and let's use the quadratic formula to see what we get. So x equals opposite b plus or minus square root b squared minus 4 times a times c all over 2a. So 2 times 1, so that's just 2 on the denominator. Excuse me, 2. All right, let's simplify that. X equals 2 plus or minus. Looks like we're going to have a negative under the square root. This would be 4 minus 12, so -8. and that tells me my other two solutions are going to be imaginary. Now, with imaginary solutions, remember we want to write them in terms of I. So again, let me clean this up a little bit, get some space for that. All right, so let's simplify this complex number. Remember, a negative in the square root we can represent with I outside the square root. So we can write this as 2 plus or minus I times the square root of 8 divided by 2. And square roots, well, we can rationalize the square roots. Or excuse me, simplify. We'll simplify the square root. Square root of 8 is not a whole number, but square root of 8 is the same as the square root of 4 times the square root of 2. Square root of 4 is a whole number, that's just 2. Square root of 2 not a whole number, so I'll leave that as square root of 2. And we can reduce all these 2's. 2 divided by 2 is just 1. And then 2i divided by 2 would just be I. So I can write that as 1 plus or minus I times the square root of 2. And that will bring me up to 5 solutions. So I have 2 imaginary solutions here, or complex numbers, represented by the plus and the minus, my 2 different values. And then I have the 3 real solutions, including a repeated solution of 1 and 1. So that brings my total up to 5, which matches with my 5th degree. Let's look at a couple more theorems. One theorem is called the complex conjugates theorem. If you remember, complex numbers are some real number plus or minus some imaginary number. And if you remember, the conjugates would be a plus bi and a minus bi are considered to be conjugates of each other, one with addition, one with subtraction. So the complex conjugates theorem says if f is a polynomial function with real coefficients, meaning no imaginary numbers involved, and if we're told that a plus bi is an imaginary zero of f, then its complex conjugate, a minus bi, must also be a zero of f. Because when you multiply complex conjugates, they get rid of the imaginary number, and thus would give us real coefficients. There's a similar theorem that we'll look at next. We also have an irrational conjugates theorem. And if you remember, irrational numbers would be something like a real number plus an irrational number, square root of b. And its conjugate would be a minus square root of b. And when you multiply irrational conjugates together, they get the irrational numbers all cancel, and we're left with a rational number. So if we have that f is a polynomial function with rational coefficients, so no irrational numbers involved, and if a and b are rational numbers such that the square root of b is irrational, then if we're told that a plus the square root of b is a zero of f, then a minus the square root of b must also be a zero of f. So if we're asked to write a polynomial function f of least degree that has rational coefficients, so no irrational or imaginary coefficients, and a leading coefficient of 1, and we have zeros of 2 and negative 2 minus 5i. Well, if I have only rational coefficients and negative 2 minus 5i is a 0, according to the complex conjugates theorem, negative 2 plus 5i must also be a 0. Now, because it's least degree, we're going to leave it at the 3 zeros. We don't need to add any more than that. So if I have a 0 of positive 2, that would go with a factor of x minus 2. If I have a 0 of negative 2 minus 5i, well, that would go with a factor of x minus that whole quantity. Now, if I subtract this whole quantity, minus a negative 2 would become plus 2, and minus this double negative, minus a negative 5i, would become plus 5i. So that will be another factor. Then my third factor comes from this 0. Notice if I stopped there and just multiplied these together, I would still end up with imaginary numbers in my solution, which my polynomial should not have any imaginary numbers in it. They should all be rational coefficients. So I need to include this in a factor as well. So x minus negative 2, so become plus 2, and then minus a positive 5i, so minus 5i. And those are the three factors of my polynomial. So to find the polynomial, I just want to multiply those out. Now it's going to be easiest to multiply the imaginary ones together first, because all of the imaginary numbers should end up canceling. I could multiply this using the vertical format or the horizontal format, whichever you prefer. Now the way I have it set up, I'm just going to go ahead and do the horizontal format, where I'm going to distribute first of all the x to all three terms. And that would get me x squared plus 2x minus 5ix. Now I'm going to distribute the 2 to all three terms. The x, the 2, minus 5i. So that would give me plus 2x plus 4 minus 10i. And finally I need to distribute the 5i to the x. So that's plus 5ix. I'm going to line that up here since I'm running out of space. 5i times 2, that's plus 10i. I can line that up over here. Those will cancel. And then 5i times negative 5i would be negative 25i squared, which I'll put over here. All right, let's combine like terms. Let's see, x squared, I only have one of those. 2x plus 2x, so we have 4x. Those cancel, and I have plus 4, and then remember, right here, I squared is negative 1. So negative 1 times negative 25 is positive 25. Add that to the 4 here, and I get plus 29. So there's the product of those, but I still need to multiply it by the x minus 2. Go ahead, set that up, multiply, see what you get. I'm going to multiply using the vertical format. So I'll start with the negative 2. Negative 2 times 29 is negative 58. Negative 2 times 4x is negative 8x. And negative 2 times x squared, negative 2x squared. Now I can move over to the x. X times 29, we get 29x. X times 4x, we get 4x squared. Plus sign in there since the 29x is positive. And then x times x squared, we get x cubed. Everything's lined up where we can just add like terms. And here I get a polynomial, leading coefficients 1, of least degree, that would end up having the zeros that were given to me. 2, negative 2 minus 5i, and then the negative 2 plus 5i. Descartes' rule of signs says that if we have a polynomial function with real coefficients, then the number of positive real zeros of f is equal to the number of changes in sign of the coefficients of f of x, or is less than that by an even number. The number of negative real zeros of f is equal to the number of changes in signs of the coefficients of f of negative x, or is less than that by an even number. Let's look at what that would mean with the previous example and the polynomial that we found. All right, the function we found in the previous example was x cubed plus 2x squared plus 21x minus 58. And I know already that it had one positive real zero at positive 2, and then it had 2 imaginary zeros, so it didn't have any negative real zeros. Well, let's look at this using Descartes' rule of signs. If I look at the coefficients of f of x, I can see it goes positive, 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 and then negative. So it only changes signs one time, from a positive to a negative here. That means it has one positive real zero. Or if I subtract 2 from that, I'd end up in the negative, so it has to then have one positive real zero, because I don't have any other options that are 2 lower than that. Now, for the negative real zeros, now this actually back up here, that does match with our positive 2 being our one real zero. Now for negative real zeros, we want to look at the signs of f of negative x. Well, if I plug in a negative value and cube it, it's going to be negative. If I plug in a negative value and square it, it's positive, times a positive in front is positive. So that's one sign change. If I plug in a negative value for x here, that would give me a negative times a positive, so that would be negative. There's another sign change. And then the negative 58 is still negative. So what I would have with plugging in f of negative x is I have 2 sign changes, from negative to positive, positive to negative. So with 2 sign changes, that means that there are 2 negative real zeros, or subtract 2 from that, 0 negative real zeros. And for this particular problem, we saw that we had 0 negative real zeros because our other 2 zeros were imaginary. If I'm looking for positive real zeros and negative real zeros on the graph, well, I just want to look and see where the graph crosses the x-axis. If I have a graph that does something like that, well, let's look at the positive real zeros. I can see it has one here, another one here, and another one right there. So it has 3 positive real zeros. For negative real zeros, I just want to look and see where x is negative, and I can see it has 1 negative real zero. So that's easy enough to just look at the graph and see what zeros are positive and what zeros are negative. That concludes section 2.7, the fundamental theorem of algebra. Thank you.